Now we've already studied Boyle's law. In this video we're going to look at three different laws: Charles' law, Gay-Lussac's law, and Avogadro's law. Charles' law states that the volume and temperature of a gas are blankly related. Well, how do you think they're related? As the temperature of a gas increases, what do you think will happen to the space that that gas takes up? Will it get bigger or smaller? So if we increase the temperature, the gas volume, you guessed it, will also increase. So temperature and volume are directly related. And of course, that assumes that moles and pressure stay the same. So if we were going to graph Charles' law, it would look something like this. The relationship between temperature and volume. As temperature increases, it's going this way. Volume is going to also increase, so it will go that way. So it will be a linear shape. And remember, this relationship is called direct. Now let's look at a kinetic molecular theory explanation of Charles' law. So here's our initial conditions. Here are the gas molecules inside, moving around in straight lines, random motion in all directions. And you can see that they're spaced far apart. And remember, these whooshies mean that it's moving. And this one here is colliding with the wall of the container. And when it collides with the wall of the container, it exerts pressure. So that's the initial conditions. Now what happens if we increase the temperature? Now you've already learned that increasing the temperature of a gas causes them to go faster, because temperature is a measure of kinetic energy, and kinetic energy is the energy of motion. So more temperature means they're moving faster. So to illustrate that they're moving faster, we're going to add longer whooshies to the end. Well, you can see that it's going to be colliding more often, and it's going to be colliding more forcefully. So the volume, in this case, is going to increase. So just like we'd expect, the temperature and volume are directly related. As one goes up, the other goes up. Now we of course have a formula for Charles' law. V1 divided by divided by T1 equals V2 divided by T2. So these are the initial volume and temperature of the gas, and these are the final volume and temperature of the gas. So be sure to write that down. We'll be using it a lot. And don't forget, the temperature must be in Kelvin. Let's look at Gay-Lussac's law. The pressure and temperature of a gas are blankly related. Well, how do you think they're related? If the temperature of a gas goes up, what do you think will happen to the pressure? Yeah, you guessed it, it will also go up. So temperature and pressure are directly related once again. And of course that assumes that moles and volume remain constant. So how would we graph that? Well, of course, it's the same as before. If temperature goes up, pressure goes up. So the line, it's linear like that, and the relationship again is called direct. So let's look again at the kinetic molecular theory explanation. So here's our initial set of conditions, and here's our final set of conditions. You can see that because the temperature has increased, that the gas molecules are moving faster. But this time, the gas molecules are contained in a rigid container. So the container is not able to expand. But because they're moving faster, once again, the collisions will be more frequent and more forceful. So here's our formula. This is the initial pressure and temperature of the gas sample, and that is equal to the final pressure and temperature of the gas sample. And once again, the temperature must be in Kelvin, not Celsius, Kelvin. All right, Avogadro's law. The moles and volume of a gas are blankly related. Well, how do you think they're related? If we add more moles of a gas, what do you think will happen to the volume of that gas? Think about maybe like blowing up a balloon, for example. Each time you breathe into a balloon, you increase the number of moles inside that balloon. And what happens to the volume of the balloon? Well, it goes up. So moles and volume are directly related. And again, that assumes that pressure and temperature remain constant. Now, if we were going to graph Avogadro's law, it would look exactly like the other two graphs. Because moles and volume are directly related, it also has a linear shape. Let's do a kinetic molecular theory explanation for Avogadro's law as well. So here's our initial set of conditions. Now we're going to increase the number of moles, and let's see what happens to the volume. So we just added more moles, and more moles will make more collisions, and it will make the volume of the container get larger. So moles and volume are directly related, and we have an equation that follows the similar pattern. This is the initial volume in moles of the gas sample, and that's equal to the final volume in moles of the gas sample. Now we've looked at three laws: Charles' law, Gay-Lussac's law, and Avogadro's law. Hopefully you've noticed that the relationship for all three of those laws is direct. As x goes up, y goes up. So we have four laws that we've looked at. The three we just studied now, their relationship is direct. The one we studied before, Boyle's law, that relationship is inverse. So Boyle's law will be the only inverse relationship we study. The other relationships are direct.